Now I've pushed the button. So we've got it. So if I were putting together right now a study guide, this is the kind of information that we would have in it. The other part is, if you look at it, this is the summary in your book. I'm going to focus in on it. And if I were doing my homework, one of the things that I would probably do if I don't have a hard copy of the book or I don't have a loose leaf copy of the book is print out the summary page. Because it's going to do two things for you. One, it's going to tell you which sections stuff is in. And two, it's got all of your equations in the summary. May not necessarily be in the way that you're going to need them for a problem, but it's got everything in there for the summary that you have. So if you don't print out anything else from your text, the summary pages are going to be really, really helpful. And then certain examples are going to be very, very helpful. Okay? So the summary is a really good way of looking at the chapter. Okay, on Friday, we talked about contact forces. We defined the laws. We even talked about drawing free body diagrams. I think we even talked about the definition of a Newton. So we're about to do that again. So if I do force is equal to mass times acceleration. And remember, this is the simplified version of Newton's law. My units are going to be in kilograms, meters per second squared, and that's defined as a Newton. Forces are newtons and pounds. Remember, mass is kilograms and slugs. And if the problem gives you an object has 50 kilograms and I need to get it into a weight, that's going to be, my weight is going to equal mass times gravity, which is going to be my 50 kilograms times my 9.8 meters per second squared, and that should give me like 490. .490 newtons. If my problem gives me newtons, do not multiply by gravity. Okay? Because inevitably on a test, I will see somebody do this. I'll give you the problem that you have a 50 Newton object, and because you're so much in the habit of doing this, you're going to go ahead and put 50 newtons and you're going to multiply it by gravity. That's going to give you some weird thing like 490 Newton meters second squared. Your units will help clear up. If you keep track of your units, you'll prevent yourself from doing that mistake. So this already gives you your object as a force. So you want to, this is something that's a common mistake when you're working your homework. They give it to you in pounds or they give it to you in newtons, and you don't have to necessarily figure out the weight. You don't necessarily have to figure out the weight, and you want to make sure that you're not hurting yourself for doing that. So now this, of course, is for Earth. If I'm on the moon, if I'm on Saturn, the acceleration due to gravity is going to be a little different. One of the things that we talked about, and you want to get in the habit of, because drawing your picture makes all the difference in the world, is you want to do force body diagrams. Or they're also called free body diagrams. So if I have a block on a table, and I'm going to apply a force to that block, I want to draw that force there. I will also have a force due to gravity, and I will have a normal force. And if I have a force due to friction, it's a resistive force to the motion. So on my block, right now as it stands, I've written everything that's there. So working these problems, what you're going to want to do is you're going to read the problem. Then you want to draw your picture. You want to label your forces. And then you want to list your data, and you can put your data in there. So if this happens to be, well, I'm going to give this to make it we'll go ahead and make it a 60 kilogram object. Okay? So if I want to do that, I want my force due to gravity is going to be mg. So I'm going to put in my 60 kilograms times my 9.8 meters per second squared. That's going to give me 588 newtons. Because I know my force due to gravity, I'm using Newton's third law that this is equal but opposite. So my normal force is also going to be 588 newtons. This force is going to be my mass times my acceleration. And this force, if I have friction, is going to be the coefficient of friction times the normal force. So if I label everything, I've got my equations, and I have the information that's known. And what we're going to do in this problem, okay, this is a simple problem. I read something on Facebook this morning. You will all appreciate it because this is a simple problem. I'll tell you about it after we do this problem. And I'm sure I'm going to get nods of heads this morning on that one. All right, so we want to find, the problem is going to ask us if we apply a 10 Newton force, what's the acceleration of the block, assuming that I have no friction. Okay? They'll say that there's no friction, or disregard friction, or use some words to that effect. So I can put in 0 for friction. And we want to find acceleration with a 10 Newton force. So I'm going to put down my equation. Force is equal to mass times acceleration. I'm going to solve for acceleration. And now I'm going to plug in my numbers. So I've got my 10 newtons divided by my 60 kilograms. And if I put in my newtons, that's kilograms, meters per second squared, divided by kilograms. Kilograms cancel. And I'm going to get .167 meters per second squared would be the acceleration. If you're doing this on the test, drawing your picture gives you partial credit. Getting your equations down gives you partial credit. Showing you work is going to help you out, because what will happen is somebody, because we've been using 50 or whatever, put a 50 in there, get the wrong number, has done everything right, except plugged in the wrong number in their calculator, or did something terrible, like plugged in your calculator 1/50 and got a bad number here, but you wrote it correctly here, you're going to get most of the credit for the problem. So that's going to help you out on a test. All right, so this was the meme on Facebook this morning. They used math class. So it said, in class, the problem is 5 plus 5 is equal to 10. In the homework, it's something like 746 plus 555 minus 683 divided by 452. We'll go ahead and do it just for grins and giggles, because I don't remember the actual number. Where's my divided? This would equal 1,299. On the test, 2 cows are in the pasture, and one is red and the other is moving. What's the price of beef 3 days from now? Or something to that effect. And I went, I bet all my physics students feel exactly the same way. And I kind of chuckled. And I thought you guys would get a good chuckle out of that this morning, because I know everybody in my class feels that way. All right. So let's do another one. We've got a football player. Accelerates from rest to 10 meters per second in 0.5 seconds. If the player is 90 kilograms, what force does he hit the opposing player So we got a football player that's going to accelerate from rest to 10 meters per second in 0.5 seconds. And we want to know the force with which he's going to hit the opposing player. So go ahead and draw your picture. We got the guy going from here, from 0 to 10 meters per second in 0.5 seconds. And we've got the opposing player sitting out there. And we want to know the force that's going to be hit. So in this case, a free body diagram is not necessarily going to help me out. But I might know my equation is going to be force is equal to mass times acceleration. I know the mass. The mass was given to us in the problem. That's 90 kilograms. I don't know the acceleration. So hopefully this other information will let me calculate acceleration. So remember, we got V is equal to V initial plus AT is one of our kinematic equations. We start out at rest, so that's 0. I've got velocity and I've got time. So I can rearrange this to solve for acceleration. So acceleration is going to be velocity divided by time. This is going to be my 10 meters per second divided by my 0.5 seconds. It's going to give me meters per second squared, so life is good. This works out to be 20 meters per second squared. There's my 90 kilograms, my 20 meters per second squared. It's going to give me 1,800 newtons. Oh, that looks better on the screen. Is that clearer on the screen for you guys over there?
Yes. Yes.
At least it's not focusing in and out like it has been. Yay. This is why we can't forget our kinematics. Okay? This is why we can't forget our kinematics. Because we'll have problems like that. Sometimes we'll get common units. Oh, by the way, the second week of October 7th through the 13th, I think it is metric week, just in case you wanted to know. Gravity, just in case we get pounds, is it going to be 32 feet per second squared if we get pounds? So you can figure out mass. So every now and then you'll get different problems that'll be in pounds. So we could do like a simple pound. If I've got a 10-pound bag of sugar and we want to know the mass on the moon, the gravity on the moon is 1/6 gravity on the Earth. So if I want to do that, I'm going to take my 32 feet per second squared divided by 6. Gives me 5.33 feet per second squared. And if I do weight is equal to mass times gravity, or my force is equal to mass times gravity, I'm solving for mass. The force was 10 pounds. My gravity is 5.33 feet per second squared. Gives me, oh, I hate when it does that. Gives me 1.875 slugs. Because I'm working in English units. Luckily for us, most of the time we are working in newtons, so we don't have to worry about it. But to give you an idea of the difference between pounds and newtons, let's take our 90 kilogram guy that we had for our football player. So my 90 kilograms times gravity is going to give me his weight. It's going to be 882 newtons. The conversion factor is 1 newton is equal to 0.225 pounds. So 888 newtons, 0.225 pounds divided by 1 newton. Newtons cancel. is 198.5 pounds. So 90 kilograms for a football player is a reasonable number. It's a reasonable number. Okay, force is a vector. So let's work the problem as a vector. So I'm going to car, so we're going to look at the car from the top, and we're going to be towing the car, and we got two people that are pulling on ropes here, so I've got one force being applied here, I have another force being applied here. The force that's being applied here is 400 newtons. The force that's applied here is 450 newtons. This angle is 10 degrees. This angle is 30 degrees. We want to find the net force. So if I draw just the diagram by itself, this is 400 and this is 450. This is 10 degrees and this is 30 degrees. What I'm going to need to do is get my components. So this component right here, my 400, this is going to be in this direction, is going to be 400 cosine 30 degrees. This one right here is going to be 400 sine 30 degrees. Because here's my angle, this is the adjacent side, that's the opposite side. So my cosines and my sines are going to be reversed than what we normally think of because I'm working with this angle.
Bring that up a little.
I'm going to do the same thing over here. This side is 450 cosine 10 degrees. This side is 450 sine 10 degrees. This equals 200 newtons. This one equals 346 newtons. This one equals 78 newtons. This one equals 443 newtons. So now I can write it in its vector form, okay? So I'm going to write it in its vector form. So force 1 is going to be 200 newtons in the x direction plus 346 newtons in the j direction. Force 2, which is this one over here, is going to be a negative 78 newtons in the I direction, but a positive 443 newtons in the j direction. My resulting force My resulting force is going to be 122 newtons in the I direction, 789 newtons in the J direction. So that's the actual vector. The magnitude of my vector is going to be the square root of 122 squared plus 789 squared equals 798 newtons. My angle is going to be the arctangent of 789 divided by 122, which is going to give me 81 degrees, and this is from the x-axis. Okay, that's from the x-axis. So if I'm drawing my vector in my picture, it's going to be close to the vertical, but this is where the 81 degrees is. So this angle, if I'm drawing it in the same one, is going to be 9 degrees. So if there's no friction and the car is on ice and we got two people that are pulling it that way, that's the direction the car is going to go. If we want to find the acceleration on the car, and we're told the mass of the car is 8,000 kilograms, no, we don't want to use 8,000. Let's be more reasonable. We'll use 3,000 kilograms. Force is going to be mass times acceleration. We've got the force, so it's going to be force divided by mass is going to equal my acceleration, which is going to give me my 798 divided by my 3,000, which will give me 0.3 meters per second squared. And the acceleration is going to be in the same direction as my force.
How do you get these two numbers squared to be, I mean, is that what it, do you?
This right here,
do them separate?
you want to, how do I get the resultant vector? Let's go back to my triangle. So I have an x component, I have a y component, I have my resulting component. So if this is my resulting component, this is my x component and my y component. Our vector here was, I had 122 in the x, I have 789 in the y. A squared plus b squared is equal to c squared. I want to figure out what c is. C is going to be the square root of a squared plus b squared.
So I mean, do you put that all under the
All of it's under the square root.
square root and you just put it in and that's what it comes out?
Yep.
I keep having a hard time getting my calculator to get
Now
that.
now let's watch it in the calculator, because that's where a lot of you are going to have trouble, particularly on this sucker. I don't like this one, but today my good one has disappeared. All right, so I'm going to do the square root. Okay, 122 squared. This calculator, you want to make sure everything stays underneath the square root, and it's doing it. 789 squared. Hit enter, gives me 798.
Oh, it is. Yeah.
Now, if you don't have a calculator like that, you've got your parentheses. Okay, so I could do it like this. I could do it 122 squared plus 789 squared gives me that. Do a second function, square root, second function of the answer, go in. So there's another way to do it. You can use your parentheses to do it depending on your calculator. You've got to know how your calculator manipulates the numbers. You also have to remember order of operations. Okay? You got to remember order of operations.
So then how in turn do we get the 81?
The 81? Angle is equal to the arc tangent of 789 divided by 122. So on my calculator, make sure I have the arc tangent. 789 divided by 122. Close your parentheses to make sure it's doing it correctly. 81.2.
So how do I get the arctangent by doing the mode?
So mine's the second function over the tangent.
Oh, okay.
Yeah, mine's the second function over the tangent. Most calculators, it's going to be the second function over the tangent.
Okay. 583, 58. I got 58.
It should be 789 divided by 122.
Oh, I put 198. So, 81.
Yep. Yeah, and different calculators are going to do it differently. So you have to pay attention to how your calculator does it. Okay. So we talked about it, and your book chooses to do it here. But the whole idea behind Newton's forces is that if I have two masses, mass 1 and mass 2, there's going to be an attraction between those masses. And where this comes from is that the sun, you have Kepler, and Kepler was given the task of explaining Mars. Okay? Kepler was given the task of explaining Mars. So if I look at Mercury, Mercury goes around the sun, Venus goes around the sun, the Earth goes around the sun, and Mars goes around the sun. So this is Mercury, Venus, Earth, Mars. Now we talked about relative motion. Okay? So if the Earth is going around the sun this way, turns out Mars is going around the sun in the same direction, that way. As the Earth moves and progresses, we're going to be looking at Mars. So if I'm sitting here on Earth looking at Mars, one day I'm going to see Mars right there. One day I'm going to see Mars right there. One day I'm going to see Mars right there. The next day I'm going to see Mars kind of sort of in the same spot. And then I'm going to see Mars kind of in the same spot. And over the couple of days, it looks like Mars goes backwards. And then Mars goes happily along. And it's because as I'm looking at Mars from the Earth, if I'm looking at it starting over here, Mars is right there. If I look at it right there, Mars is right there. If I look at it as we get next to Mars, Mars is right there. I look at it when I look at Mars, oops, Mars has gone backwards.
Due to rotation of the Earth?
Not rotation of the Earth, the orbit of the Earth. So if I'm looking at Mars from here, Mars is not moving. Mars has got a bigger distance to go. So if I'm looking at Mars lives right here on this day. And so if I'm looking at Mars from this day, Mars is moved a little bit, but it's right there. I'm looking at it from here, Mars looks like it's right next to me. I'm coming in, Mars is moving this way, I'm coming in, uh-oh, Mars starts looking behind me. It's a relative motion problem, and this is actually called retrograde. And about 2 summers ago, we actually experienced it. You could actually watch it in the night sky. It's kind of cool. And so Kepler was given that particular thing to explain. And if you've ever gone in and looked at Earth-centric solar system models, the actual mechanical models, they have to do some weird gearing in order to explain retrograde if Earth is the center of the solar system. So Kepler said, well, first of all, let's make the sun the center of the solar system. That was one of the first assumptions that they made. Second assumption that they made was that all orbits are elliptical, with the sun at one of the ellipses. So all orbits are going to be in an ellipse, and the sun is going to be at one of the foci. That's the first assumption that he made. And it turns out for Mercury, Venus, and Earth that the ellipse is so close that the two spots, Earth's almost a circle, but the ellipse is so close that both foci are actually inside the sun. That tells you how close to being a circle. And a circle is a special ellipse with both foci at the same point. So a circle just happens to be a special ellipse. So one of the things he also said, that if I were sweeping out on this ellipse, so the time that it takes to go from here to here, and the time that it takes to go from here to here, those are going to be the same. And the areas of these triangles works out to be the same. So that's one of Kepler's laws. And he said that if I look at this, the period of my rotation is going to be, and we talk T's in period, is going to be proportional to r cubed, the nominal radius cubed. Now, like I said, for Mercury, Venus, the Earth, and Mars, we kind of look like a circle. We're kind of a squatty circle, but we're pretty close to being a circle. So this r cubed explanation works out really, really well. But Newton was trying to use these observations to discuss the Earth-Moon system. Turns out the rules still apply. And that's where we get Newton's law of gravitation. And what he says is that the force is proportional to the two masses divided by the radius squared. And then we ultimately now know that this is a gravitational constant. And we end up with something that looks like this. So basically what we're doing is I have a mass, and I have a mass too. The distance between these two is going to be my r. And I can calculate the force between these two masses. And by the way, it's an attractive force because it's a force due to gravity and it's attractive force. And G is equal to 6.67 times 10 to the minus 11. The other key part is that the mass is going to act at the center of mass of the object. Now, right now, that's something that we intuitively know, and later on in the semester, will we actually be able to calculate center of masses? But for right now, we're just looking at the forces. So if I have these two, I'm just going to be a plug and chug, right? I'm going to take the mass of this times the mass of that divided by the radius squared, multiply it times the center of gravity. The attractive force is along this line between the two masses. This is going to want to pull this way, this one's going to want to pull that way, which is what's going to give us tides. Okay? The moon is predominantly what gives us tides, but the sun also affects our tides. That's why you can have a super tide. Okay? You got that. And you also have rotation of the earth also affects the tides. So we have a lot of things because the earth is kind of a fluid object. So I can end up with why we have these attractive forces. But I want to do a problem associated with this because it becomes a vector type problem, and we'll see it again. So I'm going to put a mass, and this is going to be a 3 kilogram mass, and I'm going to locate it at 0, 0. I'm going to put another mass, and it's going to be a 5 kilogram mass, and I'm going to locate it at 2, 0. And then I've got a third mass that I'm going to put over here, and I'm going to make it a 4 kilogram mass. And I'm going to put it at, let's go ahead and make it 2, 0, because that's going to simplify life for us. Right? So this distance here is 2. This distance here is 2. And because of that, we can figure out this one, right? This is going to equal this, the length of this side is going to be the square root of 2 squared plus 2 squared, which is going to be the square root of 8, right? 2 squared is 4, 2 squared is 4, 4 plus 4 is 8. So if I do the square root of 8, oops, go ahead. Gives me 2.83. So I can I want to know the net force on this object. Okay, I want to know the net force on this object. Because we know it's being pulled towards that object, and we know it's being pulled towards this object. Because it's an attractive force. And I want to know the net force on this object. So I'm going to have one force here. And this is going to be force, to keep track of my forces, this is going to be force 3, 5. And I have a force over here, and this is going to be force 3, 4. So I'm going to calculate the magnitude of force 3, 5. It's going to be 6.67 times 10 to the minus 11 Newton meters squared kilograms squared. And I've got the 3 kilograms, the 5 kilograms, and the distance between them, which was 2 meters squared.
Ms. Woodblack,
Yep.
with the 4 kilogram, wouldn't that be 0.2?
Yeah, you're right. I wrote it wrong. I drew it. Yep. So now I'm going to plug this into my calculator. Now I do the simple stuff first and then multiply by the heavy stuff. So I'm going to do 3 times 5 is 15. 2 squared is 4. So I got 3.75. Now I'm going to multiply it by my 6.67. Now, depending on your calculator, that's where this one becomes funky. And that's also why I do it this way, and that's to the minus 11. And I hit enter. Gives me a force of 2.50 times 10 to the minus 10. .50 times 10 to the minus 10. Now, that was the magnitude that we calculated. I want to write my vector force because I'm going to end up adding 2 vectors. This is all in the x direction, so it's 2.50 times 10 to the minus 10 in the I direction. And it's positive because it's going that way. My other one, my 3, 4, I'm going to do the same process. And this is going to be in newtons because my meters cancel, my kilograms cancel. So this is 3 times 4, that's kilograms squared, divided by 4 meters squared. So this is going to be 3 times 6.67 minus 11 gives me 2.00 times 10 to the minus 10. And this is going to be in the J direction because it's all up there. So now my resultant force is going to be adding those together. I have nothing else in the X direction, so I get 2.5 times 10 to the minus 10. Hang on. And I get 2.00 times 10 to the minus 10. This is my resulting force. Which is going to have it go something like that. I can calculate the magnitude, and I can calculate the angle. So I do that, squared plus 2.5. This calculator doesn't like to deal with exponents very well, and I don't particularly like it. So this is going to be the square root of 6.25 times 10 to the minus 20 plus 2 It's going to be plus 4 times 10 to the minus 20, and it's going to be all under the square root of that. So the magnitude ends up being 3.2 times 10 to the minus 10. And the angle ends up being 38 degrees. 38.7 degrees.
And the equation of 3 and 4, should it be 2 meters squared?
No, well, this 2 meters squared is 4. I just am leaving the meter squared for the units. Yeah, I just did it as 4. Because it's 2 squared, that's 4. That one I left in parentheses.
So do you square the 4 or just?
No, I'm not squaring the 4 because I already did.
Oh, that's.
Because that side is 2. See, this one I have the 2 meters squared. The square here is only attached to the meters, so I can make sure I can cancel out my units. because the sides were the same. So if these two objects are fixed, this object is going to move this direction. Now you understand why I've harped on vectors. I've harped on vectors, I've harped on vectors, I've harped on vectors, because we use vectors a lot. We use vectors a bunch. Okay. Let's define, because we're dealing with vectors, we're going to do another vector type problem, and we're going to define the first condition of equilibrium. So what I have here is I have a lamp hanging from the ceiling. My lamp has a mass of, we'll give it a 0.5 kilogram. We're going to be a light object. But one of the things we know about this lamp is, and I've got a force due to gravity that's trying to pull this lamp down, right? I've got my force due to gravity, so that's going to be my 0.5 kilograms times my 9.8 meters per second squared. And if I plug that in, it should be 0.5 times 9.8. I think I've done this enough. Yeah, this is 4.9 newtons. But we know from experience what? Huh? What'd you say?
There's an opposite force.
There's an opposite force. Okay, we got an opposite force. So we have an opposite force. We're going to actually call that force tension, because it's tension in the wire or tension in the string or tension in the cable. We actually have tension. So we have an opposite force. But what do we know about this lamp? The whole reason we hang it up is why? I know it's early in the morning. But is this lamp doing anything?
Making light.
Making light.
It's making light, but is the lamp in motion? No, lamp's not in motion. The lamp's sitting put. That's our first condition of equilibrium, is that this is our net force, right? An object in motion remains in motion unless acted upon by another force. An object at rest remains at rest unless acted upon by another force. But that means that my sum of my forces that are being applied is equal to 0 because there's no motion. Okay, there's no motion. And because there's no motion, we're defining this first condition of equilibrium. This thing is static, right? This thing is static. I know I have a couple of you that are architecture majors, and there's something that we're going to get into called statics, and we actually look at everything here, and it's all about balancing forces in order to keep us from not moving. Okay, so this is my first condition of equilibrium. And we're going to have the sum of the forces. Now that's really cool now, because that says that for this system here, I have no motion, so that's going to equal 0, but I have tension in the cable that's going up, and I have my force due to gravity that's going down. And by experience, we know what that is. We know that the tension's got to equal the force due to gravity, and that means that the tension in the rope is 4.9 newtons. So for a simple object, we have 4.9 newtons. So my lamp, that works really well. Now, here's a fun one. Let's do a sign, right? So we got a sign. Except this time we're going to take 2 wires and we have our sign. We have the force due to gravity coming down, right? And we have tension, and we have tension. And usually those tensions are equal. Usually we're not doing something to make those tensions not equal. We know that if this is an equilibrium, the sum of the forces has to equal 0. So I have 2 tensions going up, force due to gravity going down. I've got tension in each of the cable is now the force due to gravity divided by 2. Okay. Now we got to complicate things, right? It's like my homework problem, right? So now I've got a situation like this. I've got my sign, and I'm going to put in a stabilizing against the wall, and I'm going to have my cable there, and I want to find the tension in these cables. This is tension 1, this is tension 2, this is my force due to gravity. And we're going to go ahead and give it to us, and we're going to say it's 100 newtons. This angle we're going to say is 45 degrees. So tension 1 is going to equal tension 1 cosine 45 degrees in the I direction. I've got tension 1 sine 45 degrees in the J direction. Tension 2 is just in the negative I direction. I'm going to rewrite it. It's going to be minus T2 in the I direction. And my force due to gravity is equal to 0, or is equal to 100 newtons, but it's in the J direction and it's going negative. So I'm going to sum up my forces in the X direction, and I'm going to sum up my forces in the Y direction. My forces are going to be in independent directions. So my sum of my forces in my Y direction, or my X direction's got to equal 0. My sum of my forces in the Y direction has to equal 0. So in the X direction, I have T1 cosine 45 degrees. I have minus T2. This one, I have T1 sine of 45 degrees minus 100 newtons. 2 equations, 2 unknowns. Well, I can solve for T1, so I get T1 sine 45 degrees is equal to 100. T1 is going to be 100 divided by the sine of 45 degrees. That's going to be 141 newtons. T2 from the first one is equal to T1 cosine 45 degrees. So it's going to be T141 cosine 45 degrees. And that's 100 newtons. And the reason that worked out to be 100 newtons is because I used 45 degrees. Okay?
What if you don't get anything but one, like, something in newtons and there's no angle? How do you figure the problem like that?
Well, you either have to have the angle or you have to have some other information.
You know, all I have is one piece of information. What if I saw it?
You may have had more information than you know.
I'll have to look at it again, but I kept going.
Now, because a lot of times it's going to be two equations, two unknowns, and you may be solving for the angle as well. Your unknown may be the angle. So let's look at another one. We can do a lamp. Do our lamp again. This time we're going to have, we've got it coming in, we've got it coming in, we have it hanging down. Okay? This is going to be 60 degrees. This is going to be 30 degrees. This time we're given the lamp as 1.5 kilograms. So I've got to calculate the force due to gravity. It's going to be my 1.5 times my 9.8. Gives me 14.7 newtons. We're going to call this one T1. We're going to call this one T2. My force diagram is I have a force here, I have a force here, and I have a force there. Sorry. So T2 is going to equal T2 in the x direction. It's going to be negative, and it's going to be cosine 30 degrees, as I've drawn the picture in the I direction. It's going to be T2 sine 30 degrees in the j direction. T1 is going to be positive T1 cosine 60 degrees in the I direction, plus T1 sine 60 degrees in the j direction. Sum of my forces in the x direction is going to equal 0. So I'm going to have T1 cosine 60 minus T2 cosine 30 has to equal 0. Sum of the forces in the y direction is going to be T1 sine 60 degrees plus T2 sine 30 degrees minus the force due to gravity. Now for this one, I can use a mathematical trick to help me out. I'm going to put T1s on one side, and I'm going to write it different. Okay, I'm going to put T1s on one side. So I'm going to get T1. I'm going to do the sign on top. I'm going to do T1 sine 60 degrees is equal to T2 sine 30 degrees minus the force due to gravity. I get T1 cosine 60 degrees is equal to T2 cosine 30 degrees. I'm going to divide the two equations. If I divide the two equations, T1 cancels out. Sine of 60 over cosine of 60 is the tangent of 60 degrees. And this equals T2 sine 30 degrees minus the force due to gravity divided by T2 cosine 30 degrees. I'm going to multiply both sides by T2 cosine 30 degrees, so I get T2 cosine 30 degrees times tangent 60 degrees is equal to T2 sine 30 degrees minus my force due to gravity. So I'm going to go ahead and do this. So I'm going to get T2, and I'm going to have cosine 30 degrees, tangent 60 degrees, minus sine 30 degrees is equal to minus the force due to gravity. Calculate that number. I'm about to lose you, everybody. So we're just going to calculate this number. We know that number. We solve for T2. We take T2, plug it back into this one, and solve for T1. Two equations, two unknowns. And you do have an example in your book that looks just like this.
So it turns out to be 1?
Does it? I don't know. I have to plug it in. I have to plug it in. All right. I'll see you guys at Enid on Friday.